discussed previously what little difference between those things is, that thing only I have discussed over here. This thing, convolution of ik is nothing but I cross correlated rotation 180 degrees. So here full operation for this purpose, for this equations how they are related, that we are showing, but full is not necessary. Convolution of ik is nothing is equal to I cross correlation rotation of 180 degrees of k matrix, or for case any matrix, but here k is filter matrix, so we have just shown that, and I is the input image matrix, single channel or multi-channel. Yeah, so it is related something like this. Now I think you have got the understanding between convolution and cross correlation, and how back propagation happens for filter weights, for biases in convolution layer. And max pooling also, we can assume something like this only. So for features, loss, derivative of loss with respect to features is nothing but derivative loss with respect to output, convoluted, full manner, not valid manner, full manner with filters, filter weights for support, or filters or filter weights. And if you in terms of cross correlation after rotating the k, like filters or kernels in 180 degrees. But in simple terms, convolution fully manner, and that also fully manner for this relation. So fully convolution between the derivative of loss with respect to y's and kernels or filters, filter or filter weights, we will get derivative of loss with respect to inputs or input images. So now using this equation we can give generalized version like this. For x11 it will be till depth d, and this again the number of filters depth, and these are the like inputs, number of inputs we have, or input channels. So we can just give generalized version like this. So fully convoluted between derivative of loss or error with respect to y's and kernel weights or kernel filters to get derivative of loss or error with respect to inputs or input images or input channels. So here j is nothing but dimensions, this thing dimensions, this direction depth, and I is nothing but this direction depth. It is nothing but number of filters or number of biases, something like that, as I have shown previously. Now coming to binary cross entropy loss, if we have this thing, actual and ground truth values we can say, and y predicted from neural network which we have trained, what is the prediction happens. For example, y high ranges only in the domain of 0 1 only, not between, like it's a strict atomic value, or in between also we can take. And this is the formula for binary cross entropy loss, and we can just simply show this one also has a single probability, so that we can just simply show this only, because 1 minus y also one probability. If this is 0.6, this will be 0.4 itself, right? If this is 0.2, this will be 0.8 itself. So then we will get derivative of error or loss with respect to y, matters of gradients. So now if you want to find that dE by dy1, that is nothing but we need to differentiate this one with respect to y1 for suppose. We will just write this equation. Now we need to perform derivative. Here we have yi, so that will be nothing but till yn we have, for like all the y's we need to perform, right? We will get some equation something like this for only y1. So for all the others it will be 0, because with respect to y1 we are going to perform over here. So this is actually expansion, sigma we have expanded over here for all the y's, y1 then till yn. We will only get y1 values, because for other values it will be 0. For and y1 values also we will be having y1 star, this is y1 star, and log y1 is nothing but 1 by y1, and this one 1 minus y1 star we have, and log 1 minus y1 is 1 by y1. So derivative we have performed over here, and if we will just bring this minus sign inside, we'll shift, it will come over here, because negative positive, this will become negative now after multiplication. So this is nothing but derivative of e with respect to y1, that will come over here. So this whole thing calculation comes over here. So these things are used as we have shown previously. These values we are getting these values y1, and again this is a whole matrix of matrices. Using that, we are going to we have just shown you how we can find derivative of loss with respect to case, with respect to biases, case meaning nothing but filter weights, and also with derivative of loss with respect to inputs for previous layer. It will be useful in chain rule of differentiation, will be useful for previous layer, as I said previously. So this derivative of loss with respect to output is useful in derivative of loss with respect to filter weights or kernels, and derivative of loss with respect to biases, and derivative of loss with respect to input images, which again this is used for in training purpose, and this is used for previous layers training purposes. And this is simple sigmoid activation function, and so again, activation sigmoid function ranges from 0 to 1, pass from 0.5. This is a function, and derivative of that is nothing but we will get e power minus x by 1 by e power minus x whole square. So derivative of that sigmoid activation will be e power minus x by 1 plus e power minus x whole square in denominator. It's nothing but e power x star 1 minus e power x, which is nothing but this.